back. Let us resume our discussion on the transistor level implementation of our flip flops and look into the characterization of the flip flop in terms of the delay definitions. So, we just ended last time with the discussion on delay, that if you are having an inverter and looking at the input which is having a finite rise time and fall time, the output is also going to have finite rise time and fall time and also a delay, because ultimately there is a RC time constant associated with charging or discharging of the output capacitor at the node. So, roughly we can depict these waveforms with rise time, fall time of the waveforms and associated delays. Ideally, we would like to have the clock and clock bar to be exactly out of phase, and for that, if you are having a given global clock signal, generally we like to make the clock bar or generate the clock bar using inverter. We would also like to make sure that this clock bar is exactly out of phase with the clock. So, there is no significant delay between the rising and falling edge of the clock. So, in general, in a circuit you may have a digital signal which is single ended, it is not a fully differential signal. So, the source may be single ended, and from there you may be generating clock and clock bar at different points. So, just one point to be noted is, in that condition people generally use a combination of TG and an inverter. So, you can put a TG over here which is always on. So, it can be VDD and this is set to ground, the PMOS. So, that if this is clock and you are having the clock appearing here as well. So, when there is a transition in the clock over here, there is some delay for the TG also, because TG introduces some RC delay. As a result, this point will also have some delay as compared to the input clock. So, in that case I can have the phases or the transition points of the clock and clock bar matched. So, the purpose of introducing this TG is to match the delay between the clock and the clock bar whenever you are generating the clock bar using an inverter. So, the inverter has its delay TD, likewise the transmission gate will have some delay TD, and to some extent these two delays can be matched, not exactly, but to some extent if you size it properly, the NMOS PMOS over here, NMOS PMOS here are similar dimensions and they are sized properly, the delays of the TG and the inverter can match. So, the TG output will be looking like, if you are having the input waveform coming like this, the TG output, if this is the CK, the TG output will be just the same waveform, but delayed by small amount given by the distance between the midpoints. Likewise, the inverter waveform, we expect this will also be a little bit delayed and inverted, and once again the delay will be corresponding to the midpoint. So, what we expect is that the TG delay TG is equal to T inverter. So, that the waveform generated clock and clock bar are not having shift with respect to the transition points. So, this is another point we should note while generating clock and clock bar from a single signal in a circuit. Now, once we have this definition of the delay, based on that we can try to characterize this flip flop in terms of three important quantities, that is setup time, hold time and C to Q delay. So, we are already familiar with the consequences of the C to Q delay. We have seen that if you are having a ripple counter, you are going to have n times C to Q delay in the entire chain. The output, final output bit will settle after n times CQ TCQ delay. So, in this case, if I want to assess what is going to be the C to Q delay, for that I have to see the slave phase. This is a master stage, this is a slave stage. Remember, when the clock phase is negative, in this case suppose there is a positive edge triggered flip flop, because when the clock goes high here, then the Q changes state. So, at the positive transition of the clock, the Q over here will be changing state. So, this is the positive edge triggered, and we have seen that negative edge triggered means you will have to just flip the clock polarity. Here it will be clock bar clock, and here it will become clock and clock bar. That will be a negative edge triggered flip flop. Now, in this case, if you have a positive edge triggered flip flop, in the negative phase of the clock, this latch was on, this latch was off, this data was stored, and this was transparent to the input data. Whatever data was available here, it was, this latch was on and it was transparent, this entire chain. However, this was off, and now when the clock is going high, then finally this data will be propagating to Q. This will also have the transmission through this inverter and storing the data over here. So, that when the clock is going low again, this is going to turn on and then going to have the feedback. So, the C to Q delay, if I want to define that, after the positive edge of the clock here, what is the time taken by the Q over here to settle. So, that will be given by the time taken by the data over here to propagate through this Tg and finally through this inverter to this final output. So, at that point I can say that is the Tc to Q of the inverter, that is the time or the time delay after the positive edge of the clock taken by the output over here to settle, that is going to be the Tg plus T inverter. So, if I draw the waveforms over here, if this is your clock waveform, the rising edge of the clock, the Tg will have a certain delay and therefore, the data stored over here, it will, suppose this is VDD. So, it will have a certain delay, and with respect to this midpoint it will rise after certain duration. So, this is the delay of the Tg. So, I can say Tg, and after that you have the inverter which will again have some delay. So, after the transition, after the data is passed through the Tg and available over here, the inverter will have some additional delay with respect to this midpoint. This is the T inverter, and therefore, the Tc to Q from the positive edge of the clock, that is the midpoint of the positive edge of the clock, the midpoint of the data transition is given by the total Tc to Q delay. This is going to be Tg plus T inverter. So, this is one important delay parameter for the flip flop after the positive edge of the clock, time taken by the sample data to reach Q. So, this is the Tc to Q, because data was already available over here and only one Tg delay and one inverter delay, it reaches the final output. Now, therefore, when we are trying to characterize the flip flops and trying to see the total delay in the ripple counter, it is going to be there, it is going to depend upon this two components. Now, let us look at another very important definition, which is the setup time. Now, for the setup time is the, by definition, it is the minimum duration for which data should remain stable before the active edge. Active edge means the sampling range. In case of positive edge triggered flip flop, the active edge is basically the rising edge, and in terms of the negative edge triggered flip flop, the active edge is the falling edge. So, here if I look at the definition, we are trying to see what is the minimum duration for which the input data over here D should remain stable before the positive edge of the data. So, that means that if you are looking at the data, it can change at any arbitrary point. Suppose it is coming from some logic gate, it can change at any arbitrary point, and the positive edge of the clock is coming immediately before the data transition. This is the clock. You have the clock continuously running, and at this instant what is happening is just before just immediately after, or I can say in order to denote that. So, here I can say just I will have to draw in a different way. So, let me draw the data transition at some other point where you have the data transitioning just before the positive edge. So, that my definition is that before the positive edge of the clock, what is the minimum duration for which the data must remain stable. So, here again say that suppose the data is transitioning here. So, this is the D in, and the way I have drawn the clock, suppose you have the continuous clock waveform going in, going on. Now, here just before the positive edge of the clock, the data is making a low to high transition, and ideally we would expect that the Q output of the flip flop that we have here, that should finally make transition to 0 to high accordingly, because as per the definition of the flip flop operation, right at the positive edge, whatever is the D in available, it should be sampling that. But physically there is going to be a limit. You cannot expect that if this delta is turning or tending to 0, 0 plus, even then the flip flop will be able to latch that data. So, where is that physical limit coming from? What is the minimum delay it can handle while being able to latch the data correctly? So, that depends. If I look at this circuitry, what is happening when the clock is going from low to high, when the positive edge is coming? Before the positive edge, the data over here is supposed to be stationary, and when the positive edge comes, the data over here is supposed to propagate to the final output or being sampled by this particular transmission gate. But when the data over here itself is changing just before the positive edge of the clock, that means before the positive edge of the clock came and this one completely turned off, the data over here flipped the polarity. That means it was expected that this data would also flip the polarity accordingly from low to high. If this was going from high to low, this should also have flipped the polarity from low to high, so that the final data can also be low according to the input. But of course, there is a finite delay from this D input to the final output. It will take some finite delay for this output to settle over here. And not only that, you also have a feedback transistor, and here we also need to make sure that before the switch here turns off, this input level is able to propagate through this feedback transistor and arrive at this point, so that after this turns off, you have a stable feedback operation established, and the data over here and here is stable. So, I would like to make sure that before the positive edge of the clock, any change in the data has been conveyed till this point. It has passed the transmission gate, it has passed the first inverter, and also it has passed the third inverter, and it is second inverter, and it is coming over here. So, that the moment this is turned off, you already have that stable data available over here, and it will be establishing the latching and retaining the data. So, for the C2Q delay, we did not consider the latch over here, we did not consider the second inverter over here, because there the condition is that the data should be available at the Q point. The moment the data is available at the Q point, that means you have the final output equal to the sampled input available at this point. For reliable operation, of course, we can also include the second inverter delay, so that after this is turned off, this data is retained, but when the positive edge of the clock is coming, see that after the positive edge, this is going to remain off, and therefore, this is not going to play a role in the propagation of the data from the input to the output. Therefore, we are not considering the second inverter when we are looking at the delay from the input to the output, from the input of the slave latch to the output of the slave latch. However, when we are looking at the setup time, that is the time taken by the input data to propagate till this point, we are concerned with the latching operation, means after the positive edge of the clock, when this turns off, the data over here should be stable, and therefore, we need to traverse this two inverters and arrive at this point. So, that is giving me the setup time. So, before the positive edge of the data, if there is any transition in the input, before the positive edge of the clock, if there is any transition in the input, it should be able to propagate through this inverter and the second inverter and arrive at this point, so that after the positive edge of the clock, that change level can be copied to the output. So, here what I can say is, if this if at this particular point the data transition happened too quickly, that is this delta delay, this delta is less than the this delta is less than the Tg delay plus 2 T inverter delay. That means, if this delta duration is lower than this path delay from the Tg, the first inverter and the second inverter, that means before the positive edge of the clock, when this turned off, the data has not propagated fully in this loop, data has not been stabilized at this node, and as a result, when the Tg over here gets off and this particular clock over this particular Tg over here gets on, the data at this point can end up having the reverse polarity, it can end up having the opposite polarity, and therefore, we will expect that rather than sampling a high level, it can end up having a low level. So, for this particular configuration of the flip flop, this Tg plus 2 T inverter gives us the setup time, that is the time taken by the input data to traverse the first inverter, the latch, the first inverter and the second inverter, and be stabilized at this point. So, that the moment this is turning off, you have both these data stable, and as a result, when this is turning off and this Tg is turning on, that stable data is propagated to the second stage. If this data itself is transitioning, it is not stable, and this one is also transitioning, it is not stable, it is in the transition phase, and then you are turning this one on, then you do not have a guarantee that this one being turned on and this is in the transition phase, you do not have a guarantee that it will settle to the right level, and as a result, it can end up being in the wrong phase. The data which is getting to the output, it can end up being in the wrong phase. So, this is the definition of setup time, and looking at the circuit operation, this is how we can arrive at the definition of setup time. The other, in order to look at the setup time in a little bit from a different angle, we can also see that if the data over here is not settled and you are having the clock edge going up and the clock bar going down, and of course, they are not ideal pulses, they are having some overlap in this region. So, there is a region in which both of them are on. So, there is a transition region, rise time, fall time, because of which there will be some small region where both of them are remaining on, and in that region, of course, you have the transparent, you have the first latch open and you have the second latch also partially open. So, none of them are fully closed, and if the data over here is not settled, the data over here this has some transition point, it is not settled well, this is not settled well, and this is getting closed. As a result, you can have this particular gate turning on and the data over here can end up driving the data over here. It can influence the data at this point, because this is turning off. If this turns off slightly more quickly as compared to this, and you have the data over here well settled and the data over here is not settled. So, whatever data was available over here, it will be having the on path and it will try to drive it towards the higher value. So, the value over here can get dictated by the output node, rather than this point writing to the output node, this can end up writing to the master latch. So, thereby reversing the master slave operation. So, that is another issue, and here one of the reasons why we are including this Tg is to prevent or to minimize that possibility, because if you do not have this transmission gate and you have this inverter only directly connected to the output, and you have some overlap between the clock phases, and therefore, these two are getting on simultaneously, there is a higher possibility that when this is trying to get off and there is a data transition and this is trying to set it to some value, this is not settled properly, this is just at some intermediate value, and both of them are simultaneously turning on in this small duration. As a result, you can have this inverter output influencing this output, this first latch output, rather than the data over here writing the data here and then finally copying it to this. This output can end up writing the data here. So, it will flip the master's state. So, this will be the opposite operation. We do not want the slave to influence the master, we want the master to influence the slave, but because of this overlap, you can end up having the opposite operation. So, this Tg to some extent minimizes that effect, because it is getting on when you have the the clock then further TG getting off. But once again, if you have some overlap, they can be on for a given duration, all of them can be on for a small duration together, and in that case there will be a fight. This node will be trying to influence the node over here. If this is not settled well because of the transition in the input data, if it is just transitioning while the clock transition has arrived, then this is at some intermediate value because the data has not settled. This has just made a transition before the positive edge of the clock. This is also transitioning while the TGs together are getting on because of this overlap of the clock, right. So, in that condition, this is just transitioning, it is an intermediate value, therefore, it is susceptible to be written by the previous by the slave stage rather than following the master's input, and therefore, this is very undesirable. It can once again lead to wrong latching of the data. So, we can see that if the data has arrived at least 2 inverter plus TG delay before the positive edge, we can make sure that this data has settled to the right value, and after that if we are opening the after that if the positive edge of the clock is coming and this is going on, then reliably it can be copied to the next output. So, that gives us a definition of setup time. And any question regarding the definition of setup time in terms of the transistor level operation, how is it coming from this particular circuitry. So, high level definition is this, that this is the definition of setup time, the minimum duration before the positive edge of the clock, before the active edge of the clock at which the data should become stable. If it changes after the setup time, T edge minus setup time, if the data changes after T edge minus T setup, then the latch up or the data latched by the flip flop can be wrong. So, that is the conclusion out of this setup time discussion.
So, the clock phase overlap is the main reason for this wrong latching?
No, the data transitioning is the major reason for setup time violation. So, the data is transitioning just before the positive edge of the clock, and data has not been able to propagate till this point, then this is this is not settled to the right value, it is somewhere intermediate value, and therefore, you are not sure that once this gets off, what is the value going to be here. What is adding more to the damage is that this overlap of the clock can further impart the influence of Q to this point. Even if you do not have the influence of Q to this point and this data has not settled, you do not know where it will end up. It can end up high or low because it is in the transition point. And likewise here, what can aggravate the problem is that you can have some overlap because of which this Q is having an open path, and it can, this inverter can influence this data. So, that is adding to the trouble, but the setup time violation is coming because of the change of a transition of data just before the positive edge of the clock. So, you should transition sufficiently below sufficiently before the positive edge of the clock, then only the value will be latched correctly. And then the other important definition is hold time, which is just the opposite of setup time, the duration after the active edge for which the data must remain stable, or the input data must remain stable. That means, if I go back to the waveform and look at the first case that I have drawn over here. So, here the data is transitioning just after the positive edge of the clock, and here I have to see that what is the minimum duration if the data is transitioning just after the positive edge of the clock, whether the flip flop is going to be able to latch the correct data over here. For that, once again I need to go back to the transistor level circuit and try to see from where this hold time is going to arise. So, ideally if I have these transmission gates driven by very ideal clock pulses, means which are not having any rise time fall time, clock is extremely steep, and clock bar waveform is also equally steep. So, if both of them are equally steep, clock and clock bar having very negligible rise time and fall time, 90-degree drop, and under that condition, when this Tg is getting on, immediately at that point this is getting off, this is getting off immediately, then this is getting on. Therefore, if I say that after the positive edge of the clock, this is anyway disabled. So, this does not have any influence on the data that was stored over here, and immediately after the positive edge of the clock, this is getting on. Therefore, whatever was the data level available at this point, it is going to propagate to the output. So, if the clock pulses are having negligible rise time and fall time, immediately after the active edge, that is immediately after the rising edge, this is getting on and this is disconnected from the input. The input is no longer going to influence this point, and as a result, whatever data was sampled over here at the whatever data was present over here before the rising edge of the clock, it will be reliably latched to the output. So, for ideal clock rise time fall time, 0 rise time fall time, the whole time will be 0, because for this particular configuration, for this particular latch, as soon as the clock transitions to high value, this is cut off from the input data. Input data cannot influence this node, and at that time you have the whatever data was available over here, it is contributing to the output, is getting transmitted to the output. So, for this latch, if the rise time fall time of the clock is very sharp, we can have close to very small hold time, negligible hold time, and ideally 0 hold time circuit. But once again, the moment we start having finite rise time and fall time for the clock, and you have the overlap between the clock and clock bar, once again any data transition over here just after the clock edge can propagate through the circuit over here, because of the latches being on simultaneously. So, during this overlap phase, if the data is transitioning just after the rise of the fall, or during the rise of the clock edge, if the data is transitioning, you can end up having the transition in the input data being propagated to the output, and as a result the whole time will be dictated in this case by the overlap or rise time fall time overlap of the clock and clock bar. So, if you are having a larger overlap between the rise and fall time, if the waveforms are much sluggish, then you are having a longer duration for which the output is directly transparent to the input, and during that point, despite the transition happening in the positive edge, you can have the data from D propagating to the Q, and therefore, you can end up latching the wrong data. So, the whole time will be bad in case you are having more overlap in the clock. However, in case you are having ideal clock edges, the data, even if the data over here is transitioning just after the clock edge, it does not matter, because this has been cut off and the data over here is stable. But only in case you have overlap, this particular latch can give you a finite hold time. The data must be stable before the clock edge start transitioning. So, that will be given by T overlap. So, this is the third important timing definition with respect to the flip flop, and they become very important when we are considering synchronous or asynchronous digital circuitry which are operating in mixed signal environment. Also, for digital circuitry, when we go for digital design or digital architectures where you are having large number of these flip flops, implementing state machines or implementing pipelining, etc., there also these definitions become very important, and it is important to be able to trace down these definitions to the transistor level implementation, how they are originating from the circuit at consideration. So, we stop here before we start next module.